Okay, welcome back. So do you hear me, please, and see the screen? Please write something if yes. Okay, very good. Thanks, Yusuf. So let's continue. So what we said in the first hour was that, okay, so we have some basic algorithms and data structures. They are easy enough in the sequential setting, but they turn out to be quite complicated when you have concurrency. And we cannot avoid that because concurrent systems are everywhere. So although things become more difficult, we have to learn how to deal with concurrency. And the way to do that is to take the first steps, to retake the first steps, start from the beginning, take the basic data structures and basic algorithms. But then you have to be careful that you still maintain efficiency, so that, because after all, this is one of the goals of introducing concurrency, to have efficient implementations of programs. So we would like, one goal is to maintain efficiency, but at the same time, sometimes to make algorithms efficient in the concurrent setting, you need to make them quite complicated, as we will see. So of course, at the same time, while we are doing this, we need also to make sure that the algorithm is correct. But this is not easy, again, for two reasons. First of all, because the very notion of correctness is not clear what it means. So we need to define that, have something which is acceptable, some definition which is acceptable, some which is reasonable for correctness. And also make sure that the algorithms they implement indeed are correct. And this is not easy because these algorithms tend, if they are efficient, they tend to be complicated. So there is a trade-off between efficiency of correctness, and we would like to maintain both. And as I said, all these things that I will introduce in the course will be self-contained. So, which means that in principle, you just need some basic knowledge of computer science. But all these concepts I'll try to explain intuitively. So first, of efficiency. In fact, there are two aspects of efficiency. You have time efficiency. In principle, what you want to check is that how much time it takes for the algorithm that you have designed to solve an instance of the problem. And what I mean is the following. Suppose that we take the classical sorting problem. You are given an array of some size n, and you would like to generate or sort the array. And now there are different algorithms to do that, as we know. The best ones, they run in n log n. In fact, under some assumptions, you may have linear time complexity, but say that the best ones run in n log n. So this means that if you give me an array of size n, then it will take me time, which is n log n, to sort the array. But there are other algorithms which are less good or less efficient. They may take n squared, for instance. So once you have solved the problem, you have designed an algorithm to solve the problem, you would like to decide how efficient it is from the point of view of time. And this is called the time complexity of the algorithm. Also, there is a related notion of space complexity, which means how much memory or how much space it takes for the algorithm to solve an instance of the problem. Where instance is that you fix an array of size n in the case of sorting, and then you decide the complexity in terms of this given instance of this array of size n. And the same thing with space or memory complexity, because sometimes memory is a bottleneck in the implementation of algorithms. We have some algorithms, for instance, in program verification, where the bottleneck comes from the sheer size of the state space of the program. So both time and memory complexity, both time and space complexity, both time and space efficiency are interesting. Sorry. And in fact, there is an area in computer science, a big area with sub-areas that deal with this, namely complexity theory. Of course, this is not the subject of the course, but there are courses on complexity theory. But here we need to do some kind of analysis for the algorithms to motivate why they are efficient. And then the notion of efficiency, again, will not be easy, because efficiency can be in terms of the overall system, but also from the point of view of one given thread or one given process. For instance, if you have processes that are contending or competing for some resources, for instance, a stack, each one of them should get access to the common resource in a reasonable amount of time. And this is part of the time efficiency analysis that we will perform in the course. The second notion, which is correctness or reliability, means that you would like to prove that your correctness or your implementation, your algorithm is correct. And for this, you have to define perform two tasks. First, you define the notion of correctness, you formalize the notion of correctness, and then you do the actual analysis to prove that your implementation indeed is correct according to this notion of correctness that you are currently using. And this is, again, is a science in itself. So first of all, we have to define what it means to be correct, and then to do a correctness analysis. And for this, there are methods called testing and verification. In fact, this is something that we are doing in our research in Uppsala, to do testing and efficient testing and verification of concurrent programs or concurrent systems. And in fact, correctness is, again, crucial. This is true, especially for so-called safety critical systems, like nuclear power plants or avionics or embedded systems, where you need to be absolutely sure that your system is correct. Otherwise, or in medical equipment, so you have to make sure that your equipment is correctly implemented. Otherwise, the consequences will be very severe. So these are safety critical systems, but there are also the systems that are critical from the point of view of economy, like banking systems. So correctness and security, in fact, both these are very much related and very much relevant in the design of algorithms. Again, we will do correctness analysis in a much simpler setting, namely the design of algorithms, or basic algorithms and data structures, but with the added complexity of having concurrency. So again, the two criteria by which we will judge our implementations, our algorithms, are the criteria of efficiency, both time and space, but also the criterion of reliability and correctness. And here we will not do any formal analysis as we usually do. Here we try to take it at a high intuitive level. Okay. No, so I'm going backwards now. Sorry. Okay, so this is just what we did. This, that, this. So if you go back to the overview, the outline of the today's lecture, we have done algorithms, data structures, we have motivated concurrency, we have said a bit about why it's difficult, we have defined the notions of efficiency and correctness, and now the question is how to do that, to solve all these problems. And this will be the subject of the course, in fact. So now you know the subject of the course, and now so we know the what are we going to do, and now the important thing is to learn the how, which is the rest of the course. So how do we design algorithms, basic algorithms and data structures that are efficient and correct in the context or in the presence of concurrency? Now, to do that, I will introduce some concepts which will allow us to define the notion of at least correctness, namely that of specifications, safety properties, and liveness properties. And these are things that I will reuse throughout the course. And again, these have been studied quite intensively for decades now, in fact. But here, everything will be very informal, very intuitive, just explain to you what they are and how we can achieve them in our applications in our algorithms. So I'll go through these three concepts, specification, safety properties, and liveness properties one by one. And we start with specifications. So this is a vague concept. I will try to make it more precise. What's a specification? Well, you can say that a specification is an abstract description of the expected behavior of the program. So what does that mean? Well, first of all, by program, again, just to repeat, this is a very general concept for me. It can be hardware, it can be software, it can be a distributed system, it can be some program written in some sequential language or with some parallel constructs. So, but what you do is that first, to come up with a notion of correctness, which you said was not trivial in concurrent setting, was to define what correctness means. And to do that, we will define what we mean by the correctness of the program. So we would try to characterize the expected behaviors. So what are the behaviors that I deem to be correct, that I expect the program to exhibit when I run my algorithm? And this is called the specification. And this is usually given in an abstract manner, as you will see, without giving the actual details of the algorithm or the program itself. Let me give you an example to make things concrete. Typically, this abstract description of the expected behavior is the computations performed by the program. Again, let me give you an example. For instance, if you take sorting. In fact, I say that the course is self-contained. I do expect you to know something. So I do expect you to know what the sorting algorithm is, what quicksort. I mean, strictly speaking, you don't need this to take the course, but you need some kind of maturity, of course, in computer science. So I assume that you know what sorting is. I mean, this is one of the basic things that you are supposed to know. I mean, it's a good criterion by which you can judge your prerequisites. If you know comfortable with sorting, then this is a good indication already. So what's sorting? Here we are given a list A of integers, A1, A2, AN. So I have a list. This just means that, by the way, again, I work in research very much with formal methods, but I have learned to not use formulas in slides. So the challenge is to explain everything at the high level. So once you need formulas, this is a bad sign. So this will be the level of formulas that I will write. I will write things like that, a list, but you will not see complicated logical formulas as you might see if you check my paper. So here, everything will be done at a very high level. So again, going back to sorting, what are we given? We are given a list A, and this list consists of an array, say, of integers, A1, A2, AN, as input, and then you have an output. Now, if you look at the output of a listing algorithm, sorting algorithm, it's a new list, B, of the same length, N, as the list A, B1, B2, Bn, integers, but such that the list B, the output list B, satisfies two properties. First, B is a permutation of A. Second, B is sorted. So now you're asking what's a permutation is. Again, you should know this, but if not, a permutation means that a permutation of a list of integers just means that a new list, which contains the same elements as the input list. So this means that the list B should contain exactly the same element as A, but possibly in a different order. So if you give you the input list 30587, then this is a permutation of this input list 08537. You see that you have exactly the same elements as the input list, but in a different order. So the specification of a sorting algorithm then tells you that the output list B should be of the same length as the input list A, but the new list B should, on the one hand, be a permutation of A, which means that it contains the same elements as the input list, but also B is sorted. And sorted just means that B1 is smaller than or equal to B2, which in turn is smaller than or equal to B3 until you get to the last element of B, which is Bn. So B should be the same length of A, contains the same elements, and it should be sorted. So together, these two requirements tell me that B is a sorted permutation of A. So this is a correct output of the sorting algorithm. So you see that this is a specification of the sorting algorithm, which does not tell you how you implement your sorting algorithm. It just tells you what's the expected behavior of the program. So again, the expected behavior of the program is that you take the input list, you produce the output list, which is a sorted permutation of the input list. And if you have a program or an algorithm that achieves that, then you say that my program is correct with respect to the specification of sorting. Now, we know from our first course on algorithms and data structures, there are many, many algorithms that achieve this: quick sort, merge sort, heap sort, etc. All of them, if you give them some input list, they will produce for you a sorted permutation of the input list. But they have different characteristics. They are implemented differently. They are very different. Some of them use recursion, some of them use iteration, some of them behave well in practice, some of them have very good worst case complexity, some of them have very good average case complexity, etc., etc. But a common factor, a common property for all of them is that they all satisfy the specification of sorting. So again, the specification of sorting does not tell you how you implement your sorting algorithm, but tells you what it should produce for you. So it also doesn't tell you about, at this level, it doesn't tell you about the efficiency of your algorithm. It's something which is related to the concept of correctness. So let me see whether there are any questions up to now. Again, I do something like this. I have to find the chat window. No, there is only some test message or some yes, yes. Okay, good. So I hope that you understand everything. And I will keep the level of the course like that. At least you get the impression that you understand everything, even if in reality, maybe you don't. But the important thing is that you get the impression that you understand everything. No, I'm joking. I will make you understand everything. This is my challenge. Okay, so again, to go back to the notion of a specification, it's an abstract description of the expected behavior of the program. So this is in the sequential setting. It's an example of a specification in a sequential setting. Indeed, specifications are very general. And in fact, they can be, there are two categories of specifications of expected behaviors, namely safety properties and liveness properties, and both of which we need in the course. So let's look at safety properties first. So again, if you want to learn more about safety properties, you can go to the internet. There are a lot of resources. This is just the Wikipedia, but there are many lectures, slides, videos, papers on safety properties. I will tell you what you need to know about safety properties for the sake of the course. So first of all, a specification is either, in this course, is either a safety property or a liveness property. It is always an abstract description of the expected behavior. Now, safety property is a class of properties that you usually require the program to satisfy. So what's a safety property? We say that this expression is due to, the first time I saw it was due to Amir Pengueli. He was one as a Turing Award winner and one of the main persons behind defining the notions of correctness and doing program verification. So a safety property tells you that nothing bad will happen during the execution of the program. So what can happen which is be considered to be bad? So as the name indicates, you want to be safe. You don't want to reach a bad state. So let me try to explain this in terms of some examples. Already in the case of sorting, I can tell you the safety property there tells you that you should not reach a configuration where the program outputs for you something which is not a sorted permutation of the input. But this I'll come back to later. So let me give you another example in the concurrent setting. namely a classical example, which is called the dining philosophers. Now, if you have taken a course on operating systems, you know what this is, hopefully. If not, I will explain to you what it is. And this is not something that we are going to study in this course. I have just an example to tell you that this notion of a specification of safety property is a general concept. What's a dining philosopher? Again, the problem is well studied, and there are a lot of resources on it in the internet. So here I will explain to you how I see the dining philosopher problem. So I tried to draw this in ticks, but I failed miserably. So I'm cheating. I'm just copying some picture from the internet. So the problem is a classical one. It is used to illustrate many problems that arise in the area of concurrent programming. And this is, most of these problems are related to processes or threads that run in parallel and that share some resources. So in this case, you have a number of philosophers that are sitting around a table, as you see here. And from time to time, they start eating. So normally, the default mood is that they are thinking, and maybe they are discussing. From time to time, some of them will become hungry and try to start eating from the plate, which is always in front of them and which is always full with food. How this is done, we will abstract away from the problem. But in order for a philosopher to eat, he or she needs to acquire 2 forks or 2 chopsticks that he shares with his neighbors. So if you look at any philosopher here, you see that it has on the one hand the right, say chopstick or fork, that he shares with his right neighbor, and a left chopstick that he shares with his left neighbor. So if this philosopher gets hungry, in order to start eating, he needs to acquire both these 2 chopsticks. And in such a case, if the neighbor gets hungry, he has to wait until he has finished eating and put down the chopsticks on the table again. So if you look at one philosopher, you see that the state eating means that the philosopher has acquired both the right and left chopsticks. Okay, so why is this interesting? Well, because I told you this is used to model concurrent protocols where you have processes which are modeled by the philosophers. They are sharing resources that are modeled by the chopsticks, and they are competing for these resources, because for a processor or for a philosopher or for a process to get access to the shared resource, it should be free, that is not acquired by the competing processes or the competing philosophers, which are his immediate left and right neighbors. So usually when we analyze such a system, we first create an abstract model. And this is my model to illustrate this problem. Here I have 5 philosophers, which I illustrate or model as circles. And they share 5 chopsticks, which I model as these thick lines. So if you look at the philosophers, they are modeled by these circles here. So we have philosopher number 1, number 2, number 3, 4, and 5. And then if you look at the chopsticks, they are modeled by these thick lines in between the philosophers. For instance, this chopstick is the left of the philosopher number 1 and the right of philosopher number 2. And for one to start eating, it needs to acquire the right chopstick first, followed by the left chopstick, and then starts eating. Okay, so when we create formal models for such problems, and this is something that we do quite a lot in our research, but it will not be the subject of this course, what we do is that usually we model such processes by transition systems. So I will not go through the details, but I can tell you abstractly, each philosopher in this example has 3 states. So the green state is the default initial state of a process, of a philosopher, which means that the philosopher, or the process, if you wish, is thinking. The blue state, which means that the philosopher is hungry. And the red state, which means that the philosopher is eating at the moment. Now, if the philosopher is thinking, then it can at any time go to from the green state to the yellow state, which means that it has become hungry non-deterministically at any point of time. But in order to start eating, the process needs to acquire the right stick, followed by the left stick, and then after which it can start eating. So this means that the transition from the, if you wish, the yellow state to the red state is guarded by two conditions, namely acquiring the right stick followed by the left stick in that order. So now I have a particular implementation of this protocol in which a philosopher acquires the right stick first, followed by the left stick. Now there are different implementations, but I choose this one to illustrate what I want to illustrate in this lecture. So let's see, look at the system, what happens. So now, initially, all the philosophers are thinking. So what you can see is that in such a system, you can reason about a global configuration of the system, where a global configuration of the system is defined by the states of each philosopher. So initially, the configuration is that all the philosophers are thinking. So this means that all of them are in their green states. They are all thinking. Now, according to the protocol, what can happen is that some philosopher can get hungry. So, for instance, the first one can become hungry, which means that it changed state to hungry. Now it's in its yellow state. And the goal for this philosopher is to enter the red state, that is a state eating. But to do that, it needs first to acquire the right stick, which is what it has done here. But remember, we have a concurrent system. So this means that these processes are operating asynchronously. So at the same time, some other process may become hungry. So say philosopher number 4 becomes hungry, which means that it changed its state from green to yellow. But to enter the red state again, it has to first acquire the right stick and followed by, the right stick followed by the left stick. So acquire right stick here, and then acquire the left stick like that. So now you see that number 4 has acquired both chopsticks, which means that now it can move to start eating, which is the red state here. So this is a typical execution of the system. So in particular, number 5 now, even if it becomes hungry, it cannot enter the eating state because its resources are busy. The needed resources are busy. And the same for 3, because at least it has one resource which is busy. While 2 can still acquire both sticks and make one weight, etc. So you see that there are a lot of interactions between these philosophers. There are a lot of interleavings of the behaviors, of the processes that are possible in such a system. And this is the only thing I want to show you here. So if you wish, if you have such a concurrent system, you see already that you have some complications. You need to reason about global configuration of the system. This is defined by the individual configurations or states of the philosophers. They can be in different states. And an action of the system is defined by the actions of the philosophers, which can occur in any ordering, subject to the restrictions imposed by the fact that the resources are critical. So sometimes a process or a philosopher cannot move because the resources it needs are taken. So in this case, in fact, number 1 can indeed acquire the left stick and it can start eating like this. Now let's go back to the initial state and see one interesting problem that arises in a naive implementation of this protocol. So as we said, initially, all the philosophers are thinking. Now, suppose that number 1 becomes hungry, good. Now it needs to acquire the right stick, good. But now, because we have a concurrent system again, now number 5 can become hungry. And it changes state to yellow. And now it acquires the right stick because it has to follow the protocol. Now number 4 can become hungry and acquire the right stick. Number 3 can become hungry and acquire the right stick. And number 2 finally can become hungry and acquire the right stick. In fact, this protocol allows this process. So now you see what happened here is that now at this point, each philosopher is waiting for its neighbor. So no philosopher can proceed because each philosopher is waiting for its left stick, which is being taken by its neighbor. So this means that each philosopher is waiting for the others to proceed. And in such a case, the whole system cannot progress because each philosopher is waiting for the neighbors, at least according to this naive implementation of the protocol. So if you have given an assignment where you need to implement this, you should be careful because now you have entered a deadlock state. And indeed, this is a safety property. So nothing bad will happen during the execution of the program. Now something bad has happened, namely that you have reached a configuration where the system has deadlocked. So again, as a specification of your program, you can say that I don't want my system to deadlock. Remember that this is an abstract description of a property that has nothing to do with the actual implementation of the protocol, just as an abstract property. And this, in this case, this property is not satisfied but because you do indeed reach a bad configuration, which is a deadlock state. In fact, sometimes we say that safety properties are equivalent to reachability of bad states. So each safety property can be expressed, characterized by a set of bad states. In this case, the set of deadlock states. So the bad states here are the deadlock states. So we say that a safety property is satisfied if and only if the system does not reach a bad state. And in this case, in this particular case, in this particular specification, absence of deadlocks is equivalent to the non-reachability, if you wish, of bad state, where a bad state is a state where deadlock has occurred. Okay, so this is the bad state, and this is the deadlock state. So this is an example of a safety property in the concurrent setting. Now, if you go back to the sorting problem, as we said, a bad state is a state where you reach a configuration where the output you have terminated, but the output of your sorting algorithm is not a sorted permutation of the input. This is one example, because here you have the input, and this is a permutation of the input, but not sorted, because, for instance, this 5 violates that, and the 7, in fact, violate the sorting property. So in this case, the safety property tells you that, and this is a typical safety property for sequential programs, is that the bad state is a state where the program has indeed terminated, but with a result in which the computation does not satisfy or the result that you produce does not satisfy the specification, in this case, the sorting specification. And this is an example of a safety property in the sequential setting. So do you have any questions up to now, please? You see? No? So I think I will stop here today. I will continue on Thursday. So up to now, this is just an introduction to the subject of the course. So on Thursday, I think is the next lecture, I will start with the course proper, and I will introduce abstract data types. I think it's important that, in fact, it's important even you understand the overview, because it gives you a feeling for what problems we are solving, why we are solving them, why they are difficult, why we are formulating them like that. So all this is connected together, and together it gives you a coherent picture of what we want to achieve in this course. Again, as I told you, I will upload all the lectures to YouTube. So today I have to check with some other teachers how to do. So it will take maybe until tomorrow, hopefully later today. But from now on, from the next lecture on, the lecture will be uploaded the same day, immediately after the lecture. And if you have any questions that you don't want, or you don't, you get questions, or you come up with some questions later when you look back at the lecture, you can email me also. And of course, you can ask during the lecture also. And I will upload the slides to the student portal. And for those of you who have, there are a couple of students from other countries that do not have access to the student portal, and you are welcome to contact me, and I will try to share with you in Dropbox so that you can download the slides. And the slides are in Keynote, but I will also export them to PDF. So you can download them either in Keynote or PDF, but you will get a better performance. I think the animations are better in Keynote, but I will take the animations into the PDF also. But I think it's more efficient in Keynote, but it's up to you. So now I think Sarbojit would like to talk to you. So I don't know, Sarbojit, you can just start using this meeting, yes? And introduce yourself and maybe say something about the labs. Is that fine? Are you there, Sarbojit?
Yes, I am here.
So I will now just shut up. Let me mute myself.
Okay, so can you hear me well? Hello, hello. Yeah. So I am Sarbojit Das. I am a PhD student in Uppsala University. And also TA of this course. So yeah, so I am. So I will take the labs and correct your programming assignments. That is my duty in this course. And you have, as you already know, you have three theory assignments and three programming assignments. And you roughly have 1.5 week time to finish your assignment. And okay, so yeah, so I will talk about some general rules for doing assignment. Uh, After handing out the assignments, we will probably have a lab session where you can ask questions about the assignment, or if you have some doubts about programming in general, maybe. Uh, yeah, so you can ask in those sessions. And for the assignments, we'll use C++ for programming. So so yeah so we will so when you submit the assignment, you should follow the instructions written in the assignment questions in the assignment. And you should you should do the assignments individually, because it's fair, I think. Because we are not taking exams. And so you upload your assignment in the student portal, and you have to attach uh, instructions how to run your program, C++ program, in a PDF file, and also your source C++ source code, of your program. And So I think assignments will not be very difficult because you will just have to implement some data structures like sets or lists and in a multiple thread settings, and you have to check if they are check their performance and analyze why they are performing good or bad compared to each other, something like that. And you have to pass the course. You have to pass all the assignments, and if you fail in one assignment, you can do retake submission, but it will be later in April or June, as Parosh said. Yeah, I think that is it. So if you have any questions, you can ask me right now, or you can email me in my email. So my email is already attached in the slide today. Yeah. Mm, so someone asked, will we need to run the programs on the university servers? No, you can run in your machine. So yeah, so this the someone yeah, so you can run your program in your machine and show the running time. So the mm, how do you say, the assignments will, in the assignments you will be asked there to compare 2 or 3 algorithms. So you can run those 2 or 3 algorithms in your machine and say which one is faster. So it doesn't matter which machine you use, uh, because faster algorithms are will faster in any kind of computer. So you can use your machine. Yeah. And you have to submit the source code and the instructions how to run your program. But they can run on Windows. Okay, say C++ program, so you can, I think you can run in Windows. Yeah. Mm, but I never used Windows for programming. So if you were comfortable in using Windows and doing programming, you can use. It's up to you. Doesn't matter. Mhm. Okay, more questions?
Okay, then thank you everybody and see you later next lecture.
Okay,
Bye for now.
so bye everyone.
Okay.